In this video, I'm going to discuss the reactions of alkynes. And so these are going to be the addition reactions to alkynes. So where the pi bonds in this triple bond are actually reacting with other things. And so, as I said in the previous video, a lot of these reactions are going to be very similar to what we saw for the alkenes. And so I'm not going to spend as much time on them. I'll be able to get through all of these in this video today. And so I'm not going to go through like the mechanisms in a lot of detail, but I'm going to point out the ways in which these reactions with the alkynes differ from those with the alkenes. And so, as I said, many alkyne reactions are similar to alkene reactions because they involve the pi bonds. So these will undergo these addition reactions. And this converts a pi bond and a sigma bond into two sigma bonds. And since sigma bonds are stronger, this is generally exothermic. It's because a stronger bond is one that's lower in energy. And so going from a pi bond and a sigma bond to two sigma bonds, we are going to two bonds that together are lower in energy than the two bonds on the reactants. So having two pi bonds means that up to two addition reactions are possible on a single alkyne. So some conditions allow for addition to stop after a single addition, while other conditions give a double addition. So because we have two double bonds, we can do up to two additions across that same bond there. And so we can look at the energy of these bonds. So an alkane sigma bond is about 347 kilojoules, where the alkene double bond is about 264 kilojoules, and the alkyne double bond is 226 kilojoules. And so we see when we go to these alkane single bonds here that we are going to a much lower energy here. So this is sort of the energy that you would have to put in to break these bonds is essentially what these approximate energies are talking about here. And so yeah, like I said, we're breaking a pi bond and a sigma bond. So a pi bond on our triple bond here and a sigma bond on this reactant here to form these two sigma bonds that I have in red on this one right here. We can do the same thing with another one of these reactants to form this alkane product here from our alkyne product. And so just like with our double bonds, we can do hydrogenation on our alkynes. And so we have this triple bond here, so it's a 1 to 2 molar ratio here. We still use a platinum, palladium, or nickel catalyst, and we end up adding these 4 hydrogens across this bond to end up making the single bond here. And so with these efficient catalysts like the palladium, platinum, or nickel here, it's usually impossible to stop the reaction at the alkene stage. So if we wanted to just go from a triple bond to a double bond, this would be difficult or impossible to do if we are just using this setup here. And so we have to use these different catalysts in order to get just the double bond. So obviously with the double bond, there are two possible ways to do it. We can get the cis or the trans double bond. And so if we want to get the cis alkenes, so we do hydrogenation of the alkyne, which can be stopped at the alkene stage using what's called a poisoned catalyst. So it's just partially deactivated, usually with some other kind of, some other kind of compound mixed in with it. So it has sort of a contaminant in it. So a poison catalyst is made by treating a good catalyst with a compound that makes the catalyst less effective. And so for the cis alkenes, we can use what's called Lindlar's catalyst, so named after somebody named Lindlar. So it's a poisoned palladium catalyst made from barium sulfate coated with palladium, poisoned with quinoline. So there is this nickel boride here is a newer alternative to Lindlar's catalyst that is more easily made and often gives better yields. But we'll be sort of looking at this using the Lindlar's catalyst. And so this has the quinoline here. It has our barium sulfate here. And it has our palladium here. And then we are adding this hydrogen right here. And so we will be adding the hydrogens onto these two carbons here in the same direction to get our cis product right here. And so this is done by having, just like with the alkene, our hydrogen will adsorb to this palladium catalyst, and then we can bring in our reactant right here. And so the carbons will bond to the hydrogens that are adsorbed onto the catalyst, and we can then form these new bonds right here while breaking this bond right here in our triple bond there. All right, so then if we want to do the trans-alkenes, we want to use the sodium and ammonia here. So we're making a trans-alkene, so these hydrogens will be added opposite to each other on these double bonds. And so this is kind of an interesting mechanism here because we're using both carboanions and free radical carbons. And so what we're doing is we're taking sodium metal, so it's just the sodium metal, and putting it in ammonia. And so this will actually then pull with the electron off the sodium, getting to the Na plus right here. And so then we have what is called a solvated electron. So it's essentially an electron that's sort of held in the solvent as if it was, like similar to, I guess, like a proton in acids, in Bronsted-Lowry acids. And so this electron is actually sort of dissolved in the ammonia here, and it makes a deep blue solution. So it actually looks like this. This is what this solution looks like. It might be kind of hard to see, but you can see there's kind of this dark bar here where the sodium metal has been put in the ammonia, and as that sort of starts dissolving into this ammonia here, it becomes this deep blue color. And so then we can use that to add these trans double bonds across our alkyne triple bond. And so we put this into our sodium ammonia solution, which will have these electrons dissolved in it. And so this will come here. It will bond to that carbon right there. So we use the single arrow since it's just a single electron. The electrons from this triple bond will then move over here. And so we end up with this carboanion here on one carbon, and then the carbon free radical on the other carbon. And so the carboanion, it has a pKa, well, before it becomes the anion, when it's protonated, it has a pKa of 44, while the ammonia has a pKa of 32.5. And so this is a stronger base than this base right here. And so these electrons can actually come grab that hydrogen, the electrons then move onto the nitrogen like that, and we end up with this vinyl radical. And then we have this nitride ion right here. And so this vinyl radical is most stable in the trans conformation. So if we looked over at the beginning here, so I showed the electrons coming down from this side going onto that carbon. It could have been that it went like this, and so we would have ended up with the cis conformation or the cis isomer, but it's actually more stable if the electrons go onto this side of the carbon rather than on the top of the carbon here. And so we end up with this right here where we have this hydrogen adding right there coming off that ammonia. And so our R groups are opposite each other, so in the trans isomer. And so we now have this trans isomer here. We bring in another one of these solvated electrons, and so that will come and go right there. We end up with another vinyl anion right here. These electrons can then come grab that hydrogen, we are forming another amide ion while forming our trans-alkene right here. And so that is how we can make our trans-alkene if we want to add hydrogens across that triple bond to make a trans-alkene. So we have these two ways of making our alkenes, one which will make a cis-alkene and the other one which will make a trans-alkene here, both made from our alkynes. All right, then we have halogenation of alkynes. So this is going to be pretty much the same mechanism that we saw for the alkenes, except now we can add it in these two possible ways here. So with the alkenes, we added this across a double bond. Now we're ending up with a double bond with these halogens here, either in the trans or in the cis isomers right here. So taking a look at a little bit more of a concrete example, we're adding this bromine across here, across this triple bond. And so we can get the trans isomer here, which is going to be the major product, and the cis isomer here, which is going to be the minor product. And that's going to be because when this bromine attaches to it, we're going to have something that looks like this. So our carbons here, and then that bromine will be up on here like this, where the other bromine is going to want to come in from that side right there. And so just like with the alkenes, it's going to favor this conformation right here, the anti-conformation. So if 2 moles of the halogen add to 1 mole of the alkyne, we can get a tetrahalide. So something that looks like this, where we have halides on both, or 2 halides on both of the carbons that were involved in that triple bond. And so sometimes it can be difficult to keep the reaction from proceeding all the way to the tetrahalide, even when we want it to stop at the dihalide. And so you would probably have to take very good care to make sure that you have the right mole to mole ratio and the right conditions and things like that in order to prevent it from going to the tetrahalide rather than one of these double halides here. All right, so we can also do addition of hydrogen halides. So rather than just the halogens, we now have the hydrogen halide, so HCl, HBr, HI, things like that. And so we're adding it onto this terminal alkyne right here. And so we end up with the Markovnikov product. So we go through this double bond intermediate, but then we do a second addition and end up with this, where our halides are on the more substituted carbon right here. So we have the R group right here and the H group right here. And so we end up with the Markovnikov product from that. So this is just looking at a more concrete example here. So we have the 1-pentyne. So we're going to have the bromines end up on this carbon because it has an R group rather than just a hydrogen coming off of it. And so we end up with the Markovnikov product, the 2-bromo-1-pentene. Then if we do an internal alkyne, what we get are a mix of products. So we can have the bromine end up on this carbon right here because both carbons are now bound to these R groups, so neither of those is going to be preferred, and we will end up with the E and Z isomers of it. So we will end up with, so the bromine could be sticking off this way or this way on here, or it could be sticking off this way or this way on here. And so we will get a mixture of those products. And so this happens because we go through this carbocation intermediate here. So just like with our alkenes, so this hydrogen is going to add on here. So we have the electrons from this triple bond going through that carbon. It comes over here. The electrons move over onto that. And now we have this right here where the cation is going to be more stable on the more substituted carbon. And so this will then come and bind onto there. And so we end up with this right here with our Markovnikov product. But just like with the double bonds, we can get the anti-Markovnikov product, and so we can do this using this peroxide in a free radical mechanism here, and so we will end up with the bromine bound onto the least substituted carbon, just like what we saw when we were doing our alkenes and doing this free radical mechanism there. So again, just pointing out that a lot of these mechanisms are the same as with the alkenes with the double bonds, so I'm, kind of moving fast through these things. If you understand the mechanism for the alkenes, then you will understand how to do it for the alkynes as well. So we can also do hydration of alkynes to ketones and aldehydes. So we have our terminal alkyne right here. We bring in water with this mercury sulfate right here in H2SO4, so in acidic conditions. And so we end up making a vinyl alcohol, which is called an enol, and that will go through keto-enol isomerization, and so we will end up with our ketone here. And I'll go through that mechanism here in a few minutes. And so the mechanism for this is that we have the electrons from this triple bond coming and grabbing this mercury ion right here. So we end up with this vinyl cation. This water will come bind to the cation right there. So we end up with this intermediate. Another water can come in, grab the hydrogen there, the electrons move down onto the oxygen, so we end up with a hydronium ion right here. And so now we can have the double bond here can actually come up here and grab this hydrogen, and so this will go back to being water. And so we have our hydrogen now bound onto this carbon, so this hydrogen is bound onto this carbon right here. And so this has this resonance structure, so we can have the electrons from this come down onto here to get rid of that carbocation, so we end up with the positive charge here on our water. And so then we could bring in another water here. So, this is happening in water. So we have plenty of these around. So we can have this grab that, the electrons move onto there, and so we end up with this vinyl alcohol right here. So this is an enol. And so the enols will tend to be unstable, and they will isomerize to the ketone form. So we have the enol right here. So we have this acid catalyzed keto-enol tautomerism. And so we end up with this right here with our ketone carbonyl oxygen there. And so we can look at the mechanism for that. So we are in the enol form right here. We'll have these electrons from this double bond come to that carbon, come and grab that hydrogen there, so we end up with the hydrogen bound there. So we have the electrons then come down here. We end up with the hydrogen like that. The water will come grab that there. The electrons go to the oxygen there, and so we end up in our keto form right here. And so that's the acid catalyzed keto-enol tautomerism. I'll talk about the base catalyzed one here in a little bit. All right, so we can do hydroboration oxidation of our alkynes as well. And so in this case, though, we want to use this boron species here called dicyamelborane, where this SIA here is the sec isoamyl or cyamyl here. And so the use of this di-sec-isoamylborane is because it adds only to it one. So if you remember from the alkene videos, we can get multiple alkenes binding onto our boron species. And so if we did that on a triple bond, though, we could then have the same boron species adding onto our alkyne twice, and then sort of getting rid of that triple bond, or getting it all the way down to a single bond, where all we want to do is get it down to a double bond. This amyl here is just kind of a holdover from an old common name for these 5 carbon species. So we see that this has these 2 5-carbon species on it, and so that's why that's where that amyl comes from there. So like I said, this prevents the addition of 2 borane molecules across the triple bond, and it gives the anti-Markovnikov addition of water across the triple bond to make the enol. Then the enol is quickly converted to an aldehyde by the base catalyzed keto-enol tautomerism. So what we see is this sec isoamyl here is going to add onto this carbon right here, while the hydrogen from it will add onto this carbon, so we end up with this vinyl borane right here. We bring in our hydrogen peroxide and the sodium hydroxide here to generate this unstable enol form. Then we will do our base catalyzed keto-enol tautomerism to get to this. And so the keto form is actually an aldehyde in this case. And so the base catalyzed keto-enol tautomerism works this way. So this base will come in here, it will grab that hydrogen, the electrons move onto that oxygen, so we end up with this. Then we will have this collapse down here. The electrons on the double bond here will move onto our carbon, so we end up with this carboanion right here. So this can then grab one of the hydrogens off of the water here so that we are forming this hydroxide. So we're reforming our catalyst, which is why it's the base catalyzed keto-enol tautomerism. And so we end up with our keto form right here. But I can see now that I actually had this on here incorrectly. So I put the R right here. It should be over here. So this should be the R on this. This should be a hydrogen. Same with on these ones. This should be a hydrogen. This an R. This a hydrogen. This an R. And so we end up with our aldehyde right here. So this then should be our R right there. Yeah, it should be that way. So we end up with our aldehyde form up here. And so that is the base catalyzed keto-enol tautomerism. All right, so we can also do oxidation of alkynes. And so we can do this just like when we were doing it with the alkenes, we can do this with the permanganate here. And so we bring in our alkyne right here. This is in water. That's neutral pH, not heated or anything. And so we end up putting these 4 hydroxyl groups on here, but then we will quickly lose 2 waters and end up with the diketone here. So there are carbonyl groups on neighboring carbons in this case. So this is on an internal alkyne right here. If we do it on a terminal alkyne, we go through this same intermediate here, lose the 2 waters, then we have this short-lived ketoaldehyde right here. So this doesn't last for very long. It quickly becomes a keto acid. So it quickly becomes oxidized into the keto acid because this potassium permanganate here is a strong oxidizer. So this ketoaldehyde is going to be very short-lived and you can't isolate it from this. All right, we can also do oxidative cleavage of the alkynes using the permanganate, so similar to when we did the oxidative cleavage of the alkenes. So now we're putting in this strong base here, this potassium hydroxide, and we are heating it up. And so now we are going to split this into these right here. We can add HCl and turn it into 2 different carboxylic acids. And just like with our alkenes, we can also do this with ozone and this ozonolysis of alkynes here. So again, the reaction mechanism is going to be the same as for the alkenes. It'll just happen twice. And so we go from an alkyne here to 2 carboxylic acids by adding first ozone, then in a second step we add water so that we will then protonate these things. But anyway, that was everything I wanted to talk about for the alkynes in this video. So again, the reaction mechanisms for all these, which I didn't go through most of them in much detail because they're pretty much the same as what we saw for the alkenes. But the biggest difference between the alkenes and the alkynes is that from the alkenes, we can, when we're doing the addition reactions, we're only forming alkane products. So, singly bonded products, where with the alkynes, we can go to alkenes and to alkanes. So we can go from the triple bond down to the double bond, and then we can go from the double bond down to the single bond between carbons here. And so the biggest difference is these things we want to do to try to get it to stop at the double bonds. So, for instance, the catalytic hydrogenation to cis alkenes, where we want to use these Lindlar's catalysts, or if we want to do this metal-ammonia reduction to trans alkenes, so we want it to stay at the alkene stage, at the double bond stage. So we have to do those things if we want it to stay at the double bond stage. And so, yeah, again, we want, if we want to get these double bond products, then we have to sort of control our reactions in certain ways in order to get it to stop at the double bonds. And so there's also what we will see, and we'll talk about these more in future videos as well, are these keto-enol tautomerism. So there's the acid catalyzed and base catalyzed keto-enol tautomerisms. But yeah, anyway, that I don't want to drone on too long. I hope you found this video helpful, and I will see you in the next one.